let's say, from being quadratic to maybe being somewhat linear. By the way, any questions so far or any comments?
I think this is super cool. That's my comment.
Yeah, thanks. So I have writing some things here, and to be fair, what I was doing here was sort of a bit reverse engineering, in the sense that I just, let's say, what did I do? First, I take the P matrix that represents the pairwise totals here, and then I write here some examples of how they could be. So, for example, this is the P matrix, and suppose that, and those values here that are inside here, they are, let's say, what happens is if you take the pairwise between two users, like say user A, B, C, and user A, B, C. So the pairwise total between two users is always going to be one of the elements of those. And I'm supposing also that, let's say, each user did give two donations. And the idea is, let's say, we want to compute delta P here. There are some ways of approaching that. Let's say we could calculate delta P through an imperative approach, but we could also, for example, take the time and try to create a linear algebraic formalism of that, so that you can represent a transformation through vectors and matrices. And I don't want to dig in deep exactly how I got into that, because, I mean, it's really grinding. It's really, let's say, getting what changes, try to find mathematical representations. Sometimes you know the mathematical representations, other times you need to research, and it's not exactly a linear process. Just to give an example of non-linearity on that process, I also have been working here on representing the simple quadratic match. And the simple quadratic match would be essentially that m value here. So instead of having that m function of a grant, we would have a m vector. And I am interested in calculating the delta m. And the simple quadratic match is essentially getting that p term here, the pairwise total, and assuming that it's equal to 0. So it's the quadratic match with that term. And I got into a algebraic formulation for that, and it's kind of cool because you could use that permutation matrix here. It's a super cool object, really. But I won't dig in that because maybe it's too nerdy. But anyway, that's an object that, let's say, before digging into that, I didn't even know that existed. But by looking, for example, on the vector representation of M and how it should look when you have a new contribution, you can try to reason about, let's say, what are the operations that you need in order to make that, and research the mathematical objects that, let's say, could serve as building blocks for that.
Hey, Danilo.
Anyway, hey.
I think it's not too nerdy. Can we take a moment to open up the permutation matrix? What is that?
The permut. Yes. So let me see. I mean, I definitely need a digitizer pane. I think it could come in handy here, but let me try to explain how it works. So the thing is the following. Suppose that, let's say, you have a matrix here like M. Let me see. I'll actually see here. So maybe the most important object to reason about is the CT and C. So let's see how it is. So this is a matrix. This is not a square matrix. The idea is that, let's say, if you take that object here and take the dot product by its transpose, you are essentially getting, let's say, I mean, if you take the transpose, you can generate a square matrix of that. The thing is, depending on how you rearrange the rows or the columns, you could get different. There is a physics term for that. You could expand different vector spaces. I'm trying to think here how I can explain that without simply digging too deep. But anyway, I think that a key thing to consider is that, let's say, if we want to, the idea is that, let's say, we want to get M here through C. Let's say C is the contribution matrix. So let me explain exactly what is the contribution matrix. Each row here is a user, and each column is a grant. So for example, if you get the first row and the first column, you have the amount that user E minus, E lower has donated to grant A upper. So this is a contribution amount. This is another contribution amount. This is the contribution that user B has donated to grant A. And this is the contribution of what user C donated to grant A. So this is the contribution matrix. This is and the way that you could calculate that through our model and so on is to take the contribution sequence, aggregate over all user grant combination, and then let me see here. Yeah, probably there is some matrix operation that you should do, but anyway, this is the matrix object that, let's say, does the full description of what's happening on Gitcoin Grants. .C. This is our input for anything that we would like to do. And actually, when we talk about, let's say, delta P or delta M, okay, delta M here. Essentially, what we want to know is the following. How M changes or how P changes when we let's say, introduce a vector matrix C into C. Let's say how it changes when, let's say, C transforms into C plus C lower, as you can see here. What changes? And so as I can see here on C, I've created another matrix here to represent that, but at least that, let's say here, user A has donated an additional amount of V to A. So every time that you see W, you're seeing the amounts before the new donation, and V is the new donation. And going back to here, for example, I've put here a vector representation of the match. So what this tells us? It tells us the following. If you pick grant A, the match is sort of that summation, but just a disclaimer that formalism is not entirely accurate because I'm not taking the square root, because we would need to put a square root here, another square root here, another square root here. I didn't do that because, doing that in the linear way is already difficult enough. So first time, let's say, getting the basics done, and then we can think of what object we could do so that we can implement that square root element by wise. And for the grant B, we would also have the same thing. And when we are talking about delta M, which is, let's say, how M has changed once I've put that new contribution, essentially what I'm doing is, let's say, adding that to the grant A. And why is this value? It's because I have computed M for the new contribution and I took the difference. So let's say those two here are hard truths. And the problem is how you represent M, how you represent the transformation of M, or better, how you have a closed form for delta M given C. So that's our problem here. And this is actually an open problem. I didn't quite finish that yet. But anyway, the idea of having that P and why we do that in such a way, maybe I should do a step-by-step for that. But suppose that, let's say, we drop that P term here. We only have C transpose dot C. What's going to happen? If you get a C here, C transpose is essentially, instead of having the rows as users and columns as grants, we have grants as columns and users as columns. So it's a bit hard to see. I can see it clear because I'm sort of trained to do that, but I can imagine that could be a bit hard to see. But anyway, the result of doing that is that, let's say you take that and take that. You are going to have a 2x2 matrix here. And those guys are, yeah, I definitely need the editors are paying. But anyway, one problem by doing that transpose is that, let's say, if you get at of the matrix that gets around that, you are not going to have, let's say, a format in which you can sum that to that. Maybe the pairwise gives, yeah, I think that maybe yeah, I definitely did that digital pain. Anyway, I don't want that to be the focus because there is a lot of being work on that, and also because let's say I really want to get on code because let's say I already have a suggestion here of let's say what we could do that could do a speed up without needing all that algebraic formalism. Perhaps the algebraic formalism would be better for maybe next week, and also it's going to be to have a mathematics working group. So
Can I ask a question?
yeah.
This is Jay Rush. If I understand, and I apologize, my math degree is 37 years old, so forgive me for this. But you want to create a matrix of donations per grant and per user. And by doing that, then all the remaining calculations become basically matrix operations. Is that the fundamental idea? And then I have a further question.
That's right.
Yeah. So you kind of put it in a matrix, and now you're doing multiplication of matrices with vectors or vectors with matrices and so forth.
Yeah, that's right.
Right. Does that, do you think that that's faster? Because if you have, I know there's about 1,200 grants and there's probably, I don't know, 10,000 users. Do you think that would be faster? Is that, or your goal is to try to find a mathematical way to show you what would be faster to get the same result? Is that fundamental, what you're doing?
Yeah, I think that's one of the goals because if you have those matrices formalism, you can make use of linear algebra toolkits, and it's way easier to make more parallel. There are a lot of there are several. It simply becomes easier to integrate with the existing scientific computing ecosystem.
I see. Okay. And do you have this matrix of grants and users yet, or no?
Oh yeah, TC, we do have.
Okay. Yep. Thanks.
Yeah, and let's say I already have, for example, a matrix expression for P, but for M we don't have. I have a suggestion here for the simple quadratic match, but I'm still working on that. But anyway, the most important one would be to have a matrix formalism for, let's say, for the quadratic match with pairwise. But this is probably going to be a difficult problem. Because that M matrix here that I've been, let's say, playing with, it has a simplification that I have dropped the P term here. But this is not what Gitcoin is using. So that simple quadratic metric exploration is really just to get a basic intuition of how we could represent that. But having that representation is still an open problem, and I don't expect it to be exactly easy.
One of the things I've been thinking about this, why this would be so advantageous is because most of these matrix representations would be really sparse, and there's like a ton of algorithms for like computing this type of stuff really fast for sparse matrices. Like most people are only contributing to a few grants, I'm assuming.
Yeah, and I also expect to be sparse, and I think this is another reason of exploring that.
In a weird way, the sparseness of this matrix is kind of what we're trying to explore, because we're looking for non-sparse parts, it seems, or something like that.
Yeah. And also I think that, let's say, exploring that a bit, I mean, once you have the matrix formalism, it's way easier to identify, let's say, what's the delta. It's more explicit, let's say. Because in the end, we're only interested in the deltas. But anyway, this is still a working thing, and let's say a practical way of maybe doing some actual hacking today that I was thinking about would be to, let's say, to implement that calculation here of delta p. And let me see here. Yeah, and also there is a thing that I have been investigating that, let's say, just by having that formalism here, it's possible to drop one of the loops if we are clever here. I put here why. Let me see why. Yeah, there is a dependency. Yeah, I still need to create an example about that. Let me try to remember here. So it's a bit complicated to visualize, but let's say if you get that M matrix here, you could sort of understand as a triangular matrix that keeps being filled up. Because let's say one of those here, you have two objects here that depends on the grants. Yeah, actually it's not a matrix, it's a tensor.
I think, like, are you trying to say, it seems to me like matching pairs of contributions or anything like is commutative, so you don't have to go both directions. So it's just like the lower like triangle half of like each like, you know what I'm saying? Like it would be symmetrical.
Yeah, exactly. It's symmetrical. Not only that, but let's say if we do have a new let's say if we have a new contribution, this is sort of analogous of adding a new index here on bot summations. Let me try to make it more explicit. Yeah, so let's say if you have a new contribution, the difference the difference is going to be on the summation here. And if we take the difference, then let me see how I could rearrange that. So there is we just need to iterate that first here one time. So actually we could drop that. Do you understand why I don't need to iterate? I just need to do that once? Because, for example, if when I get the M matrix and the delta matrix, let's say if I have 10 contributions and then I have 11 contributions, this is going to be 11. But if I take the delta, I could, let's say, I could leave the 10 first out because I'm just getting the delta. So actually this would be 1. Oops. And then there is this term here that we need to see how it changes. So we just need to iterate once, but I think that this one we should pick everyone. Yeah, because out there what, but at the same time the authors, yeah, there is a problem in there. Actually, this is done 2 times. Yeah, it's done 2 times. Yeah, it's a bit confusing, but the reason of why I did that is because, let's say, this is the M function when you have a new contribution, the contribution C. And what happens is that, let's say, instead of iterating 10 times here and 10 times here, we need to iterate 11 times here and 11 times here. So the first thing when you get the delta is that, let's say, we don't need to iterate here 11 times. We just need to iterate here 1 time. But once we get here, we need to iterate 11 times. So this is the first way of seeing that. Another thing is that when we get here, for the other 10 times, we don't need to iterate that second term 11 times. We just need to iterate 1 time. So that's why, for example, here I put 1 before the summation. And I put the summation here and I put 1. This is not exactly a clear-cut way. I hope that this is not confusing. But anyway, I think that this gives a basic intuition. And maybe one way of putting that is that, let's say, here, let me break down that. So I think that I'll start using Greek letters here. So let's put, get alpha here. So it's really just to break it down because it become a, sometimes we have that problem of things becoming polluted. So this is what's happening here. I put alpha and beta not in the sense that they are, yeah, they are actually constants. But the idea is that, let's say, when I get that delta here, actually I'm just, let's say, I get the last G on the first summation, and I do the summation as normal. And at the same time, I get all the others ones except the last out G's, and I get only the last G. So let's say if M is a I mean, if the object here that m depends is a matrix, we are sort of getting just the first row and the first column. It may be a bit confusing, but okay, given that, let me see if there is anything else here. Yeah, I think that's it. But at the same time, there is another thing that, let's say, if G here is the last, G is always going to be higher than E. And there is also there is this Iverson bracket here. So what happens is that one of those are going to be 0 because, I mean, this is because of the symmetry of that. So for example, on that instance here, G is always going to be higher than Z. So this is going to become 0. So alpha is going to be equal 0. So actually, we only need to care about B. So calculating delta M is essentially calculating beta. I'll put there on the end so that it doesn't become too polluted here. But anyway, at least we have some pathway to explain why I did take that, why I did that suggestion here. Yeah, and also we need the inversion bracket in here. So the idea that is, let's say, if we want to calculate delta M, we don't need to calculate M over again. We just need to take the previous M until we update that vector by doing that. And also there is a dependency G. Yeah, I didn't factor that dependency G actually. I think this generates a more complicated thing. Yeah, because this is delta M on G. I mean, that's why linear algebra algebraic formalism would be good. Because, I mean, if you have the matrix, it's way easier to you to think in terms of everyone at once. While I'm using that as a function, I don't have that global view. So actually, that time here would need to be applied over all grants. So, I mean, this is going to be a nasty vector. Yeah, very nasty vector. So let me think how this affects things. Yeah, and also there is the problem of the pairwise dots that affects everyone at once. I mean, because we have a coupled problem here. Because let's say if we have a new donation, we also update the P. And if we update the P, we also are adding a delta M for everyone. And I mean, we have dropped that term, we calculate the quadratic funding, which is already something. But I mean, this is really a toad problem. So let me try to think about a strategy. Given a new contribution, first thing, we update P by using the M depends on B, but which depends on P here. All right. Yeah, I'm thinking here, maybe I'm suspect that actually we can't do that procedure here because, I mean, M depends on P. There is no way getting ahead. If we update P, we are updating, I mean, perhaps this process is not valid because we are implicitly supposing here that P is constant across time, but this is not true. I mean, for some reason I was thinking that, but this really generates a complicator. By the way, guys, what do you understand why I'm thinking about that? Why I'm stressing about that? Any comments, questions?
I'm not like fully with the way that you're seeing it or thinking about it, but I'm sort of thinking about this. I think this is like really interesting to me, and maybe like where I'd want to do my research topic. Because I'm thinking like the way that you need to structure it is like there's some function that operates either on like the function representation or the matrix representation of the contributions to compute the matches, and then you need to basically take like the partial derivative of that with respect to like any contribution. So like there needs to be a way to either like, I don't think time series is the right way, but I think like a more like a discrete approach where like the way you guys model it, where like any contribution is the next discrete step, and then take the partial derivative with respect to that, I think would be the right way to get to like this computation, because there's some algorithm
Yeah.
that I'm still getting up to speed, so I don't feel like I have a good contribution to be like, oh yeah, like actually think about P this way, but like I sort of formulating the problem is making sense to me, if not exactly what you're talking about right now.
Yeah. I'm thinking here maybe another approach that we could adopt instead of trying to directly optimize. Maybe we could simply measure the impact of things, like because, for example, we are calculating the M here, but let's say how much of the overhead is due to the M itself and how much overhead is due to the P. Maybe just that by having some numbers gives us some sense of priority of things. I think that I will do that actually, because I mean, I don't know exactly right now if the problem is on the quadratic parity or if it's on the pairwise totals. Anyway, any more comments or thoughts?
I was just thinking that maybe I think we're gonna code this up, which might make it a bit clearer for people through that process. So that's good. I find sometimes the math is more intimidating with linear algebra. When you actually see it as a vector, it can be more clear.
Yeah, actually, I mean, if you had a linear algebra, probably it would be a bit clearer, because the thing about linear algebra is that, let's say, it gives us a global vision of things. And anyway, what I was thinking about here is maybe a better strategy would be to simply measure the performance impact that we're having, let's say, by having that P term here or not. Because, for example, if the problem is P, maybe by just having that data P, we already do a lot. I think that this is I mean, we should have that. We should need have that number anyway. So let me see how I should proceed here. So I think that the definitions is on the optimality gap folder on the definitions file. Oh no, exactly on the quadratic match file here. Oops. So we have several things here. So the most important one here is the quadratic match, where let's say you give a graph, a threshold, and it returns us the match. And maybe the question that I have right now is that by forgetting that, I have that function here called getTotals by pair. And let's say, what's the percentage of the slowness that I'm having due to that getTotals by pair? And I don't have, let's say, a head answer right now. Perhaps this is an interesting thing to investigate. So I think that one thing that I'm going to do, I think that I will simply create a new folder here called, sei lá, CAF performance. I think it's clear. I'm going to put it at the root here. And I'll create here a file called quadratic match. There is probably a better way to do that, but anyway, I just want to have a folder where I have some files and I can change things without breaking other things. So I'll create the quadratic file here and copy at the performance. Oh, okay, it's already there. Oops. Done. And maybe one thing that we should do is to simply generate some random graphs, but on quadratic fun, on the quadratic match one. The first thing that I'm going to modify here is that instead of returning the matches, actually I'm going to return the execution time. So let me import here import from time import time. This is a Python function that returns seconds since the Unix first epoch, which is about 50 years ago. And what I'm going to do here is to create two values here. So first one is going to be, I'm going to return a tuple here. And let's say it's going to be the total time and the per totals time. And the total time is equal to, let's say, T2 plus T1. T2 we measure here at the end of that function. And T1 we measure at the beginning. The per totals time, it's going to be PT T2 less PT T1. PT T2 we measure here. Oops. We measure here at that part, and PT T1 we measured it here before they get totals per pair. So this is the function that calculates the P matrix, and this is the and that matches here is the part that calculates the M vector. And the question that we want, I think it's important to us to have that number that is, let's say, how much of that slowdown is due to calculate that vector, and how much of the slowdown is due to calculate the P matrix? Because I mean, if the problem is the P matrix, we already have some leads. If the problem is calculate the vector, then we have a problem. So just to get the importance and the priority sorted out it's always an important thing. And what I'm going to do is to create a new notebook here. I'm going to just copy. I'm going to just copy the attack vector a bit test because I mean it's the one that we have worked last and probably the memory is fresher there. And this notebook is going to be the F performance diagnosis. And let's open it. Also, I'm going to change here the title. So let's put I'll put the link for the specification here. I also need to change what I'm importing here. So instead of importing of Malita Gap 1, I'm going to import the TKF performance. Okay. Now I'm loading here the data. There is also the things here about some visualizations. And I'm going to delete here so the things that I have put for the EB test that we have sorted out on the 2 weeks ago. So we need that contributions per graph here. I think it's one of the functions here. Probably I'm just going to copy and paste that. It's simple, clear. Okay, so we have our graph here now. And let's see what happens if we pass quadratic match to that graph there. Yeah, we have some numbers here. So touch time and speed time equals that. And let's see how much is speed time and per touch time. So yeah, not exactly an encouraging result because about 12 to 30%, 13% of the execution time is by calculating P. What this means that having delta P improves performance, but doesn't improve so much. But of course, there is the thing that as the algorithm is complex, I mean, complex in the sense that it has quadratic complexity, it may happen that, let's say, by having different number of nodes and so on, that proportion can change. So let's see what happens. Maybe. So what I'm going to do, instead of calculate that for just one G here, I'm actually going to calculate for several G. So the x-axis is going to be, let me think about. I will arrange 100 to 1000 and 10 steps. No, 100 steps. And what I'm going to do here is that I'm going to tell that time is a list, actually is a dict of xz, and this is quadratic match of G for G in graphs. No, it's not that.
For xi in x.
Yeah, for xi in x. And then we get that, and we put it inside it here, and xi here. And we need a threshold here. Okay, we have something here. I think that maybe we could create another dict of that. So let me make that a bit cleaner. So fxi, ffxi, if you are lucky, maybe we can create a dictionary with that. Yeah. So they start by doing that, and we could compare how much, let's say, the time of doing how the proportion changes along time. So to make it ever more clear, maybe I think that by having index is enough. So let's plot that. So line the f.reset index. The x is going to be the index, and the y is going to be the p fraction. And of course, I need to create that variable. So let me calculate that. So I'm putting a sign here, lambda p fraction equals lambda df m time, p time, divided by df dot m time. So this is how pairwise calculate the p matrix impacts the performance. It's a bit lower at the beginning. It seems to increase with time. So let's put now maybe 3,000. I think that I need to run again. That's Gitcoin. I think that way I need to generate more data. So let me put here maybe 5. Let me see if the so I'm not going to compute kf. I'm going to put n equals 100. Let me see if it's quick. Yeah, it's already slow. There is a special version of cadCAD that for a lot of hacks that I do, it runs a lot faster. The Gitcoin simulation is one of them. So let me install that. So where it's I think it's the devil one. Pip install. I always forget the command. I think that I have bought it here somewhere. Let me see. No. But I think that we could use that. But instead of being the network X1, it would be the cadCAD. So what happens is that, let's say this branch here, this is a personal repository, but there is a branch that I did some hacks on cadCAD that for some things it can run a lot faster. Because the way that cadCAD works is that on every time step and on every state transition, it does a deep copy of the state to make sure that, let's say, the contents of the variable aren't changed if you change something on the future. And I mean, doing that deep copy is needed because if not, you can introduce side effects, like, for example, the future changing the past. There is a hack that actually drops that condition. So you stop doing those deep copies, and what happens is that if you are not careful, you can change the past. But the trade-off is that, but the good thing is that, let's say, for some things, especially data-heavy simulations, I wouldn't say, I mean, that it makes a lot faster, but yeah, I would say that it drops a complexity factor, because deep coping can be an expensive operation, can be, let's say, a quadratic complexity operation too. So for some simulations, it becomes way, way faster. Let's take a bit of time here. While that don't happen, I'll run the simulation here again, but for the lower number of steps. So Python run simulation, and I think that 2000 is fine. Compute CAF, no. So when it was 1000 runs time steps here, I think that it took 2 seconds. Let's see now. Yeah, 20 seconds. So before it was 2 seconds, now it's 19 seconds. So I mean, it's not being linear. Most probably this is due to the deep copy. I'm started here. Let's see how it goes now. So 500. 3 seconds. 1000. 7 seconds. 2000. Let's see if it's going to be 14 seconds or 20 seconds. Oops, what happened here? So okay, we are restricted to 2000 for now. Actually, while I run everything again, I think that I can run another simulation here. So I'm going to run that everything again. And while it's running, I will run another simulation here. I'll go with 6000. And here I need to put that to. I don't know exactly if this is good news or not, because I mean, by 2000 steps, calculating the P matrix takes about half of the execution time. And I mean that I don't know if this is good news or not, because it's good news in the sense that, let's say, I mean, we know how to calculate delta P. And calculate delta P, it's probably way faster than calculating P itself. So yeah, perhaps it's good news. And also this says a thing, maybe improving M isn't important until we get at really, really large time scales. But I really want to know how this curve is going, because I mean, does this curve flat out at around 50 to 40%, or it keeps growing? I mean, it would be great if we increase it to 90%, because if we improve P, then we don't need to improve M at all to, let's say, to get at really large scales. And I mean, this is an important thing because due to those complexity factors, things that are very fast at low scales and things that take a long time on low scales, when you get at really large scales, it's a whole different history. Things that, let's say, you don't need to pay any attention when you are at a large scale, sometimes they simply blow up. Well, this is sort of what's happening with P. Actually, I'm going to make it. Let me see. I'm going to make it 55. Instead of having 100 steps, I'm going to do 55 so that we have a better view of that. And also, I'm going to do a scatter. Really interesting. And it's fun because, I mean, becomes slow and then it quickly. There are some scenarios here where it takes 50%. By the way, guys, any thoughts or questions about that? I just thought another thing that, by the way, is that we have the total execution time here, but we also have a section here that is only about calculate the vector itself. Maybe we should calculate that too. So pt t3 equals time and match vector time equals pt t3 less pt t2. And then I'm going to add that to my tuple. Maybe this could be a dict. Yeah, probably this is cleaner. And I'm going to need to refactor, but the good thing is that instead of having that, I consider the return just times here. And pair totals time. Let me see what's the name of the dict. Pair totals, match total time. And I'm going to assign so here m fraction. Match vector time. I think this should work. By the way, I just computed here 6,000 events, so we can have more data for the future. It takes a bit to load that pico because now we have a giant pico file here. Yeah, 35 seconds to load. Let's see what we get. So here we have the p fraction again, but I'm going to pass a list here so that we can see both at once, m fraction. This is interesting because, I mean, the m fraction also increases, but interestingly, they don't take actually out the time. Given that, I'm going to calculate another variable here that is called, let's say, the Actually, I'm going to calculate that match time fraction, pairwise time fraction, and other time fraction. This other time fraction is going to be equal, essentially, the f is essentially 1 minus the f.match time fraction and the f pairwise time fraction. I'm going to do that after that so that we don't need to run everything again in terms of calculating the quadratic function. So let us see. That's why I did that. So pair totals. Oops. And here we put pairwise time fraction, match time fraction, and other time fraction. Yeah, interesting. So by the end of that, there are some things that take 30%. To calculate the vector itself, it's 25%, and the pairwise is 50%. But this is for 2000. Let's see if we go to 4000. What do you guys think? Is the pairwise going to grow more, or the vector is going to grow more? What are your bets?
Kind of seemed like everything was asymptoting to me.
Yeah, I was gonna say the same. I think we saw the limit at 2000. That's my bet. Let's see.
Yeah, I've put to 4000. So let's see how it behaves from 2000 to 4000. I should have increased that. Oh, theory of truth.
Wow.
So the pairwise keeps increasing. I'm going to increase here so that we could go to 6000. Actually, I'm going to do 200 here because it's going to be quicker. Yeah, so the match, okay. Yeah, so apparently once things get at 2000, it sort of gets settled. And you get that log increase on, I mean, it's not log, it's actually a square root increase. It's kind of curious because when you have those square roots increases, I mean, most probably the other time fraction is being linear, and the other one is going to be square root. By the way, let's say 11 seconds. I think that if I put 50 seconds here, it will take 40 seconds. But I think it's nice to have more granularity. One thing that we could also plot here is instead of plotting the fractions, we could also plot the execution time itself. So I'm going to prepare here while that don't happen. So so this one is going to be the pair totals time. This is going to be the match vector time. And this zone here is going to be the total time. Actually, I think that I should create another variable here. Okay, it's going other time. And the other time is going to be the f total time minus df per totals time plus df point match vector time. Let me see if he, yeah, I think it went. So this is the distribution of time, and it's interesting because I think that we need a log to, I mean, we don't exactly need a log, but maybe we could use Plotly here to have a better view. So let's see, for example, what happens before 1,000 steps. So at let's say at the beginning of the simulation for 1,000 steps, I mean, we are sort of spending the same time for everyone here. The sense that, let's say, you could see that here. Actually, we spend more time for the authors. Yeah, 1,000 is here. Yeah, so as you can see, it's sort of everyone mixed together. But after 2,000, then you start to have that because, I mean, the pairwise time fraction keeps increasing cost of the author time. The match time keeps increasing cost of the author time. And then you have that curve here. And one interesting thing is to, let's say, is to make it visible the pair totals and the match vectors so that we see only the curve for the total one. It's kind of curious because look at that. I mean, it was exploding until 2050, and then you have that breakdown. I mean, this is curious. Usually you expect that, let's say, you expect those curves to be, I mean, you can expect transitions, but usually you don't expect, let's say, a thing that is complex giving away something that is lower complexity. Yeah, so after 2000, the authors, instead of, let's say, blowing up exponentially, you start to have sort of this almost linear thing. It's not linear because you can see that it's accelerating the execution time. And by the way, those units here that you are seeing on the left, they are seconds. So for example, if we get the author times here, so for example, when we have a 6,000 contribution sequence, we take the 250 milliseconds to compute the pair totals, 200 milliseconds for the match vector timing. And I mean, it doesn't seem like a lot, but suppose that let's say you have that time for computing the pair totals, that time for computing the match vector, and you have also 0.1 here for calculating the other ones. So let's say a single evaluation of the quadratic funding takes about half a second. But when we want to calculate the optimality gap, what happens is that, let's say, for each grant, we need to evaluate that by 2,000 times. And then you need to evaluate that for all grants. So you also multiply by the number of grants, like, for example, 100. This means that for calculate the optimality gap for 6,000 contributions over 100 grants, we will take that amount of seconds. And then we could divide here by minutes so that we have minutes. And then we could have hours and then days. So it will take 1 day and a half just to compute the optimality gap for that. But the problem is that, let's say, this is not linear because, I mean, if I look, for example, at the pair totals, let's have a close view on that. I mean, actually, it's somewhat linear. I mean, weird. You also have that break here. This is interesting. I mean, it's blowing up at the beginning, but after 600, it starts being it is not more a square. It becomes sort of log linear. I mean, this is unexpected actually. So this is log scale. And I think that we can see more clearly what happens here. So we have a line here that goes until 2,800, and then you have an increase on that log scale. And there is an interpretation about log scale that it is interesting. On a log scale, the slope determines, let's say, it determines the exponent of the polynomial. So just to show about that, let me see if I can find something about that. So log scale slope. This is super interesting. Let me see if I have something ready here. Polynomial. Okay, I think that this makes the message. So can you guys see here that we have a log scale on both the axes? The vertical and the horizontal. The data that, let's say, if you take a log scale, the slope on that represents the exponent of the polynomial. So for example, if you have a thing that, let's say, grows one by one, then you have a thing that grow linear. If you have something that grows 2 by 1 on that scale, on that visualization, then you actually have a function that is sort of square-like. And if it's 3 to 1, then it grows, let's say, cubic-like. But of course, this needs to be on both axes. So let's see what happens here. Yeah, so what happens? Until time step, until 1060, we have a certain pattern here that it's not exactly linear. Let's say it grows faster at the beginning and then, yeah, I don't know, but anyway, it's very close to this one here. So suppose, for example, that the execution time here is growing. Let's say it's not exactly linear, but let's say it could be, for example, something like almost a square, like for example this. Oops, something like this, or this if you prefer. And once it gets to about 2,000 sequences until 2,800, you have an increase on the slope. So at this moment, it's like things grow cubic, for example, or square-like. But after that, it stabilizes again. But one thing that to be aware about is that it seems that at the end here, it sort of becomes it grows again. I'm thinking here if there is a way of maybe, because the way that we are seeing, we are just seeing slope points, but it would be good if we bootstrap that. Do any of your guys have experience bootstrapping visualizations on Plotly or something like that? Let me see if I can search something quick. Yeah, go on.
I was just going to say, I'm not sure what you mean by bootstrapping plots.
Yeah, let me see if I can catch an example here. Something like that. You get several points. The idea that you would have, let's say, this bench that captures the variance across the evolution. Let me see if somebody has already did that. Yeah, it's not exactly quickly. Actually, this is always a problem when I want to do a visualization on Python, because I mean, personally, I think that is super useful to have, let's say, those uncertainty bands bootstrapped. Just to show what I mean. So I always find super useful to have, let's say, those bands here where you can, for example, say you can also have a measure of the variance. And the idea of bootstrapping is to, let's say, use data that you have for estimating that even if you don't have the data. It's sort of doing, it's a bit complex procedure, really, in the sense that, let's say, you get the data, you train a KDA on top of that, but it's a thing that I would like to have it, let's say, more common on the libraries, but I never find a good, quick and simple implementation of that.
Hey Danilo, I posted something in the TE Gitcoin channel.
Yeah,
Let me see.
called continuous error bands.
Yeah, we just need to see if can handle missing data. So let me see. So it's reading here, taking the X, the ebb, mod. I suspect that this one is maybe grouping data. Yeah, the data here already comes grouped. It would require a bit of time, really. Maybe one thing that we could do is maybe we could take a hole in here and take the mean. Yeah, it's better now. Hole in 5 and medium. I think medium is best, actually. And medium. Yeah, way better. Another thing that it could be useful to see also is the standard deviation. I'll remove the log here. Got into nothing. Yeah. Anyway, guys, any comments or questions about the slowness of the quadratic funding? What question? Let me see. Yeah. Yeah, but anyway, anything that we do just with P tends to improve that. So, I mean, we already have an optimizer here for the pairwise totals. It's just, let's say, instead of computing P, we compute delta P. So just by having that is... And how would work to do that optimization of the pairwise totals here? If we look on the code here, the quadratic match, we have the get totals by pair function here that simply calculates the P matrix. And the idea is that, let's say, instead of calculate the P matrix, maybe we could take the quadratic, maybe we could take the previous P as input, and then just calculate the delta. And I think that maybe we can do that. Maybe it doesn't take too much time. So let's create a new function here that is called... actually, I'm going to call that... let me think about the best strategy here. Yeah, I'm going to call that the modular quadratic match, actually. So I'm just going to copy and paste that. And one of the arguments here, and I'm going to call that the modular quadratic match. We can take the pairwise totals as argument. It's going to be a dict. The idea is that the pair totals, instead of being that, is going to be actually, let's say, no, it's actually the iterative quadratic match. Because it takes two arguments. It takes the pairwise totals, but it also should get also the new contribution. And I didn't thought yet how this new contribution should look like, but I think that maybe the new contribution should be something like that. Let me think how it should be. Maybe a dict or a tuple. But anyway, it needs the following things here. Yeah, I think it should be a tuple. Maybe a named tuple. So I'll create one. So the idea of the named tuple is that it allows us to create Python objects. It's a quick way of creating a tuple, so, but instead of, let's say, instead of you having to access the tuple by indexes, like for example, by doing that, by accessing, for example, 0 for getting the contributor or 1 for getting the grant, you could actually access fields like, for example, like that, new contribution dot contributor. So it's a bit more cleaner, really. And the idea is that on that iterative quadratic match, that new contribution, it should be a new contribution object. So I think that is a bit clearer. And don't get totals by pair instead of actually what we should need here is actually a new function. So let's say it's the update pair totals, giving the pairwise totals and the new contribution. And this update pair totals would be actually delta P here. Where is delta P? Yeah, that delta P here. This is my matrix objects. It's described here, so maybe it's a bit more easier to do. So let me see on what P depends. The P depends on the sigma here. That sigma is simply it's simply the new contribution vector. I mean, it's a certain object that it's better explained here. Sigma essentially tells how much the amount has changed for each user. So yeah, you just take, let's say, the amount that has changed for you. So it's really a vector with just one value, and the other are zeros. The other one here, the sigma upper, that thing that seems like a summation, it's that. And let me remember how I define that. Yeah, this one is a bit more complicated because you need also the contributions graph. So that pairwise totals also require G, because every time that I need C, I'm going to need the G here, because the G is the graph that contains all the current information. And essentially those are transpose difference and the dot product. So yeah. And how would be that update pairwise totals here? collusions graph, which or the C matrix, which is captured by G. We also have the once again the pairwise totals. And the new contribution. And it should return a updated pair, or better, I'll just call a new P. And the pairwise totals is a dict of users. Let me see how I can do that. So yeah, I think that a latent task that we may need is to actually take the time for getting that pairwise totals dict and transforming that into a matrix. Because I mean, if we already had a linear algebra formalism and if we were handling matrices instead of dicts, we could do simply that new P equals P plus delta P. But you can't do that with dictionaries because dictionaries are more general. So we need to do the analogy, but for dictionaries here. That's why matrices help so much. It's more cleaner to work with them. I thought they can be intimidating sometimes. And I mean, it's not exactly trivial to do that with dictionaries because essentially what I would have to do is I need to do 2 iterations actually. So actually, yeah, it's a dict of dicts. So for key P in people to items. No, at least 2 loops. I'll call that P. Do you understand why I'm doing that? Yeah. One thing that we should, I mean, if we implement that, we should implement also those. But I think that this would take a bit of time. I wasn't so sure of doing that at the first place because, let's say, on my mind, we would spend more time to calculate the M. But given the results that we have here, just by solving that P thing, it's hard to estimate exactly. But my guess is that probably this is I mean, we have a quadratic complexity here for the pair totals. The effect of dropping the complexity factor would be to essentially drop that slope here. So maybe instead of, let's say, maybe instead of having that growth here, maybe things would simply grow linearly here. So, I mean, it's pure guesswork, but I do have the feeling that just by implementing that delta P here, the time that we take for calculate the pair totals would be sort of the same time that we calculate the other times. So yeah. So let's say instead of taking 3 350 milliseconds, it may take 100 milliseconds at that current scenario, but this is guesswork. Was someone going to say something? Water? Under the water? I didn't understand.
You sound fine. Keep going, man.
Ah, okay. I understand something about under the water. And it's kind of curious because it's raining a lot here outside. Yeah. But anyway, we have 40 minutes. I would like to actually maybe to end the coding session for now. And I mean, I would like to know your any thoughts or any things. One of the things that I was thinking actually for next week is, I mean, if anyone wants to take the slot and so on, I mean, everyone is super invited, especially now that, I mean, we have several projects going on. And yeah, I would like to leave some time for us now.
First, thanks for sharing again, Danilo. I was wondering, can we maybe try to frame, is there any next step for the math working group? I'm wondering if we could formulate, let's say, a contribution or a reasonable next step here that the math working group can take on.
Yeah, so from what we have seen here, I mean, there is an important thing that is to work on that. I've showed the thematic spec. I don't know even how to start to create a formalism for updating the matching vector. And I think this could be an important thing for, let's say, for the guys that want to work on math and so on. Octopus isn't here, but he has suggested sometimes maybe we could discuss having sessions for thematics.
Yeah, as mentioned, I've cut the time for presentations to 1 hour on Tuesdays, and then we can split up to the various working groups. And so on Tuesday, there's a next session where we could have time for the math working group dedicate particularly to this question.
Yeah. And I mean, you guys saw the performance properly now. By having any advance on that, we can, let's say, right now we take hours. I know that Gitcoin takes several hours just to compute the quadratic funding for the state. And I don't want even to think about doing simulations on that. And I mean, if we can break that complexity factor, perhaps we could take seconds or milliseconds. I mean, there is lots of things that we could do once it's easy to compute.
Maybe you can also take a note in the chat channel, so results from this session, so that's easier for Octopus and others who haven't been participating today to follow up.
Yeah. I'll drop a note there afterwards.
Yeah, I think I'm on the hook for I was gonna present on the sort of linear algebra perspective of this stuff, just sort of like what's been done so far, and then I'm gonna try and come up with what I can between now and Tuesday. So maybe that would be a good precursor to the math working group. So I think this is like a really interesting thread. Is like I didn't realize until today that the complexity was so high for computing these algorithms. I think there's probably a lot of stuff that we could do either from a software perspective, but like a purely mathematical perspective more so to bring that down. So I'll keep that in mind.
Yeah, awesome.
Yeah, I think that will be a great help if we can bring that for Tuesday.
The is on Tuesday, right?
Yeah, the working session of the working group and your presentation is on Tuesday. But perhaps Danilo, you were also thinking about the academic discussion on then in 1 week, or was it just a mix-up?
Yeah.
Okay, so the session we are discussing, math working group, and your presentation is on Tuesday. All right.
Cool. And then maybe Danilo, I'll probably hit you up like tomorrow or something to just make sure, because I want to do a survey of what already is out there, and it seems like you provided a bunch of links and stuff. I just want to make sure I don't miss anything.
I'll send the agenda. Let me see here. So I have dropped a link about the agenda on the Gitcoin, and I've put on the reference the roadmap spec that HackMD document that there is those objects that I've been using on this session. So the delta
Yeah,
P is there. Yeah.
Yeah, I have all those links. I guess maybe what I'll do with my slides and then like post them beforehand or something and see if there's anything that I missed, because like I'm so new to all this. I just want to make sure that I don't duplicate some work or sort of like present on something that's like, oh no, we already figured this out.
Yeah, Andrew has been working a bit on that. I think that talking with him could be a good idea.
Okay.
Okay, any other comments on the math working groups or tasks here, or questions? Otherwise, I'd just like to make you aware of the session tomorrow, the Tech Lab with Sean. I guess we can have another round if you want to on discussing reinforcement learning. So for everyone who might be interested after Tuesday on the potential of modeling agents, reinforcement learning, to understand attack vectors, this is another opportunity to discuss this. Sean, I guess at 5 CET. Okay, at 5. Mm-hmm. Mm-hmm. Cool. All right, great. And last but not least, there is a spreadsheet. Maybe I can quickly pull it up. To note what should be your topic or your research question throughout this research group until April. And let me just check here. I hope you can see it. This is the one-stop shop document, and here's this spreadsheet working groups. And so far, we have a math working group, we have a reinforcement learning working group, and we have Jan proposed to have another work stream, Node to VAC. He'll also give some more introduction on Node to VAC next Tuesday. And feel free to just select a working group, either a working group or add a new one if you think you want to work on a different topic. It's just important that you let the others know what are you working on, what do you want to work on, and which group to join. It can be an X, can be your name, and so that we can make progress from here. And I'd also would love to have your Twitter handles, since I'd like to tag you in all our tweets. So feel free to add your Twitter handle here as well. Any questions on the working groups? Okay. Then that's it from my side. Danilo, anything else? Otherwise, close the call for today.
Yeah, I think it's good. Probably
Okay.
I'm going to, yeah, I think that's it for that session.
Okay. All right. Thanks again. Thanks everyone for joining, and see you tomorrow or on Tuesday. or on Discord, whenever in the chat.
Sweet. Thanks, Danilo.
Thank you, everyone. Ciao, ciao.
Yeah, thanks everyone.
Bye.
Yeah, I mean, we're having a huge problem, but I mean, we'll handle that through to help with everyone.
I think so. I mean, sometimes really hard nuts to crack, obviously.
But I'm optimist.
Yeah, for sure.
Just by knowing that people is the most important thing is already something.
Yeah, true. Okay, cool. See you guys. Bye.
See ya.
Bye.
Yeah, thanks guys. Bye bye.